Okay, so final question from the simple molecular substance sections, question 4. He's asking us to look at two different covalent compounds this time, both of which are gases, one of which is methane, and the second is the slightly larger butane hydrocarbon C4H10. And it's asking us to look at the differences in boiling points and explain why. So obviously we're not going to look at the dot cross diagram necessarily, we're just going to draw these in relative situations. So this is a very simplistic methane molecule. And what we'll do is draw next door to that the other methane molecule. So this is a gas. Okay, so we're going to try and boil it, but we're going to make it a liquid by putting another molecule next door to it. So that's two molecules of methane. Now, when we do that with a molecule of butane, butane is a bigger molecule. And so we're going to have two molecules next door to each other, which are fundamentally bigger. What that means is the bigger molecule of butane has a larger force of attraction between the two molecules than methane does, which is a smaller molecule. And when we are boiling a covalent substance, it's the intermolecular force between those molecules that we need to break. And because methane is smaller, then the intermolecular forces of attraction between the two molecules is smaller. So kind of the intermolecular, the IMF, the intermolecular force of attraction is smaller for methane. Obviously the vice versa answer will be accepted as well. So you could say that butane is obviously larger, etc., etc. So the intermolecular force is smaller, and so less energy is required to break it in from the liquid state. Okay, so less energy required to boil and to break those bonds. Okay, obviously, as I say, you could do the vice versa. Now, next question is asking us to just look at the carbon itself, because when we draw the structures of both methane and butane, we know that carbon can form up to 4 bonds. And the reason for this is because carbon has a valency of 4. And so it's got essentially 4 vacancies able to be occupied by extra electrons, and they can be donated from 4 separate entities if need be. To put question 3 there. So we can form 4 bonds, for example, with a hydrogen, if that was the case. But the situation here is because hydrogen has only got 1 vacancy and 1 electron, hydrogen, which is the second part of the same question, is hydrogen can only ever form a singular covalent bond and only ever will, whereas carbon can form up to 4, obviously with 4 hydrogens if need be, as in methane's case, but can form up to 4 because it's got a valency of 4 and requires the 4 extra electrons in order to become stable. Likewise, he's asking us to look at silicon, and he's asking us how many covalent bonds this could form. Now this is due to the group, again, it's in the same group as carbon, and so it's likely that that will also form 4 bonds because it's also in group 4, similar to carbon.